In a previous video, we had explored the main properties and operations involving vectors. That previous discussion is valid for any coordinate system, but it was still a bit too abstract. So now let's look at how to build vectors and their operations in the Cartesian coordinate system, which is the most popular system because it is present in most problems. Instead of following the review, which would be a bit boring, let's work in a practical way, increasing the complexity little by little. We consider in this video only one-dimensional systems described through a Cartesian system. We start by considering a horizontal axis that extends from less infinite to more infinite. Let's call it x. We also define a vector I, which is a unit vector. This has length equal to 1 and in this case which leaves the zero origin and points in the positive direction of x. We can multiply this verse by a positive scalar, that is, which gives the scale of the vector. Thus, we can define a one-dimensional vector through this equation, vector equal to the module times the versor I hat, which begins at the origin O of the coordinate system, has length and points from the positive direction of the x-axis. We can reflect this vector to the negative sense. So the vector prime is equal to minus the vector A, which in turn is equal to the length of the vector, that is A, times the negative of the verset I hat. We can also define a second vector B equal to the module B times the versor I hat. The sum of the vectors A and B will be a third vector C, which will be equal to the sum of the module of the vectors A and B times the vector I hat. If both vectors point in the same direction, vector C also points in the same direction with greater length than A and B, that is, equal to the sum of the lengths of vectors A and B. If the vectors point in opposite directions, the vector C will point in the direction of that which is the largest vector, and with length equal to the difference between A and B. We can also take the scalar product between the vectors A and B. Thus, the scalar vector will be equal to the length times the versor I hat scalar module B times the versor I hat, which in turn can be written as the product of the lengths A and B times the product scale between its versors. Since the product scales between two parallel vectors, it is equal to 1 to number 1. Where we pass the module A and B in front of the scalar product, if the versors are anti-aligned, the result is equal to -1. Another way to build the scalar product is through the module of the vectors involved and the smallest angle between them. In this case, we would have ab times the cosine of the theta angle between them. Since the vectors are aligned, then theta is equal to 0. But if they are anti-alified, we will have theta equal to 180 degrees. Then, for the first case, cosine of 0 is 1, and we reproduce the same previous result. Otherwise, with cosine of 180, which is equal to -1, the scalar product between vectors A and B will be equal to -ab. Finally, we can calculate the modulus of a vector, which is trivial in this one-dimensional case. The vector module is written between two vertical bars, where we take the scalar product of the vector with itself. The result of this will be the square root of this product. That is the square root of the module of A to the square, which is itself A, therefore positive defined. In other words, it is always positive. It's still a little abstract. Let's replace A equal to 3 and B equal to. The result is that you are seeing. But we have already exhausted all relevant one-dimensional operations. Let's go to the next level, apply Coulomb's law in one-dimensional systems.